Welcome to the Deep Dive. Today, we're really getting into the nitty-gritty of the cosmos, looking at it all through a chemical perspective.
That's right. We're using Dieter Rehder's book, Chemistry in Space, From Interstellar Matter to the Origin of Life, as our guide.
And our mission, really, is to unpack the chemistry that governs everything out there, from how stars cook up elements to maybe even how life gets started.
It's a pretty ambitious book, covers a huge range. Stellar chemistry, the interstellar medium, planet surfaces, even what's going on beneath the surface on moons and things.
Yeah, and Rehder writes it so it's accessible, even if you just have some basic science, but it's also got enough depth for, serious scientists.
Definitely serves as a great compendium.
So let's do this chapter by chapter. We're going to dig into the key chemical ideas, the discoveries, basically give you the chemical story of the universe, according to Rehder. Starting with Chapter 1. Introduction and technical notes.
Okay, so Rehder kicks off by mentioning Johannes Kepler, Astronomia Nova, 1609.
Right, Kepler. A good reminder that astronomy and physics, they've always been linked. His laws of planetary motion were just groundbreaking, based on really careful observation.
And what's really crucial about Kepler here, for chemistry anyway, is that he figured out the mechanics, how planets actually move. You kind of need that framework.
We absolutely do.
Yeah.
You need to know where stuff is and how it's moving before you can even think about the chemical reactions happening between them or on them.
Precisely. It's the foundation.
Chapter 1 also flags the big themes. The origin of life, which is obviously huge, not just for Earth.
Yeah, the big question.
And also how the basic molecules, the precursors to life maybe, actually formed in the first place.
And Rehder makes the point that you can't really tackle those questions without understanding the bigger picture, the cosmology.
The whole universe story.
Yeah, the Big Bang, how the universe evolved, what it's made of. That context is essential for making sense of the chemistry we see. It all fits together.
Okay, that leads us right into Chapter 2. Origin and development of the universe. So the Big Bang. The first few minutes, incredibly hot, dense.
Unimaginably so.
And in that chaos, only the lightest elements could form. Mostly hydrogen, about, 75%?
Roughly, yeah. And helium-4, maybe 25%, plus tiny, tiny traces of lithium-7 and a bit of beryllium-7.
And that's basically it. That's the starting material for everything else.
That initial mix is key. Almost pure hydrogen and helium. All the heavier stuff, the carbon, oxygen, iron, all that had to be made later, inside stars.
And the evidence for the Big Bang. Rehder mentions the cosmic microwave background radiation.
The CMB, yeah. It's like the leftover heat, the afterglow from that super hot early state. A picture of the infant universe, essentially.
So Chapter 2 then breaks down what the universe is actually made of, and it's kind of mind-blowing.
It really is.
The ordinary matter, the stuff we see, stars, planets, us, it's only about 5%.
Just a tiny fraction.
Then there's dark matter, maybe 21%. He mentions neutralinos as a possible candidate.
Right, one of the leading theoretical particles, yeah. Still hypothetical, though.
And the rest, a massive 74%, is dark energy.
So, yeah, when we talk about chemistry in space, we're focused on that little 5% of normal baryonic matter. But the dark matter and dark energy, they shape the whole universe, its structure, its expansion.
The dark matter provides the gravitational scaffolding.
Right.
Helps galaxies form.
Exactly. And dark energy is pushing everything apart, making the expansion accelerate. They're the stage managers, even if they aren't in the chemical play directly.
Okay, so back to that 5%. Rehder talks about the first stars, population third, formed maybe 100 million years after the Big Bang.
Something like that. And they were made almost entirely of that primordial hydrogen and helium. No heavy elements, no metals, as astronomers say.
And these were the first chemical factories.
Absolutely. Huge, incredibly hot, short-lived stars. Inside their cores, they started fusing hydrogen and helium into heavier things, the first carbon, oxygen, etc.
And when they died, there's supernovae.
Right. Massive explosions that scattered those newly made heavy elements out into space, enriching the interstellar medium.
Seeding it for the next generation.
Exactly. Which leads to population 2 stars. They formed from that slightly enriched gas, so they had a bit more metal content.
And then eventually, population I stars like our sun, younger, relatively rich in metals.
It's like cosmic recycling. Each generation builds on the chemical leftovers of the last.
So how do we know how old these stars are? Rehder gets into cosmochronometry, radionuclide dating.
Yeah, this is clever stuff. It uses long-lived radioactive isotopes like thorium-232 or uranium-238 These elements decay at a known, predictable rate.
Like a clock.
Precisely. So you measure how much of the radioactive element is left in a star compared to a stable element, like, say, europium, that's made in similar stellar events.
And the ratio tells you how long the radioactive one has been decaying.
Basically, yes. It gives you the age of those particular atoms, which effectively dates the star itself, or at least when those elements were incorporated into it.
He gives an example. The red giant, HE1523091. Its age is estimated at 13.2 billion years.
Yeah, incredibly old. Considering the universe itself is about 13.7 billion years old, that star is almost a first-generation witness.
Wow. And there are other methods, too, using extinct radionuclides.
Right. Things like iodine-129 or hafnium-182, they have shorter half-lives, so they've completely decayed away by now.
So how does that help?
You look for their stable daughter products. For iodine-129, it decays into xenon-129. So you measure the ratio of xenon-129 to stable iodine-127 in, say, meteorites. It tells you about the timing of events very early in the solar system's history.
Ah, I see. Like the hafnium-tungsten dating he mentions we'll see later with moon rocks.
Exactly. Different clocks for different epochs. They help piece together the whole cosmic timeline.
Okay, let's move into Chapter 3. Formation, classification, and evolution of stars. So stars are born from these huge clouds of gas and dust, molecular clad.
Giant molecular clouds, yeah. Gravity pulls them together, they start to contract.
And as they contract, they fragment, heat up.
Yep, the core gets denser and hotter, until eventually, ignition, nuclear fusion starts. Hydrogen starts fusing into helium. That's the birth of a protostar, which then settles onto the main sequence.
And to make sense of all the different stars out there, astronomers use the Hertzsprung-Russell diagram.
The HR diagram, fundamental tool. It plots luminosity, how bright a star actually is against its surface temperature.
And stars fall into different groups on this diagram. Rehder mentions the spectral classes, O, B, A, F, G, K, M.
Hottest to coolest, O being the hottest blue stars, M being cooler red stars, and then L and T types for even cooler brown dwarfs.
Our sun is a G2 type, kind of average.
Right in the middle, yeah. And then there are luminosity classes too, dwarfs like our sun on the main sequence, giants, supergiants, white dwarfs, indicating size and evolutionary stage.
So inside these stars, that's where the action is, nuclear fusion. Rehder explains the main ways hydrogen turns into helium. First, the proton chain, the pp chain.
Right, dominant in stars like our sun, or smaller, needs temperatures around 4 million Kelvin to get going. It's a series of steps where protons basically combine to make helium.
And the other main way, the CNO cycle.
Carbon, nitrogen, oxygen cycle. This needs higher temperatures, over 13 million Kelvin, so it's more important in stars more massive than the sun.
And it uses carbon, nitrogen, and oxygen.
How? As catalysts. They participate in the reaction cycle, helping protons fuse into helium, but they get regenerated at the end, so they're not used up, they just speed up the process.
But that means the CNO cycle couldn't have worked in the very first stars, right? The population third stars. They didn't have any C, N, or O to start with.
Exactly. That's a key point. Those first stars had to rely purely on the PAP chain. The CNO cycle only became significant later after the first supernovae had spread some carbon, nitrogen, and oxygen around. It changes how stars evolve.
Okay, so after a star uses up the hydrogen in its core, what happens? Rehder talks about the triple alpha process.
Yeah, this happens in more evolved stars, red giants, for example. The core contracts, heats up even more, maybe to 100 million Kelvin. Then helium starts to fuse.
3 helium nuclei, which are alpha particles, fuse to make carbon.
That's the net result. But it's tricky. 2 helium nuclei fuse first to make beryllium-8. But beryllium-8 is incredibly unstable.
How unstable?
It lasts for like 10 to the minus 16 seconds, basically no time at all.
So how does carbon ever form?
A third helium nucleus has to hit that beryllium-8 nucleus before it falls apart. It's a near miraculous coincidence governed by something called the Hoyle state resonance in carbon-12.
Wow. So the existence of carbon, which is essential for life as we know it, hangs on this incredibly brief moment.
Pretty much. It's one of those fine-tuning things that makes you pause. This triple alpha process is the main source of carbon in the universe.
Rehder also lists the most abundant elements, the top 10 in our solar system and the Milky Way.
Yeah, it's mostly hydrogen and helium, of course. Then in our solar system, it goes oxygen, carbon, neon, iron, nitrogen, silicon, magnesium, sulfur.
Is it much different for the whole galaxy?
Broadly similar, but there are variations. Like carbon can sometimes be more abundant than oxygen overall in the galaxy, depending on the mix of stars contributing. It shows that nucleosynthesis isn't uniform everywhere.
And how do we get elements heavier than carbon and oxygen up to iron?
Through further fusion stages in massive stars. Helium captures, carbon burning, oxygen burning, silicon burning. Step by step, building heavier nuclei. This releases energy up until you get to iron-56.
Iron-56 is the peak.
Yeah, it has the highest binding energy per nucleon. Fusing things to make iron releases energy, but trying to fuse iron into heavier things actually costs energy. Stars can't do that via normal fusion.
So where do elements heavier than iron come from, like gold, uranium?
That's where you need more extreme events, mainly involving neutron capture. Rehder introduces the different processes. The R process, rapid neutron capture.
R for rapid. Happens where?
Supernovae, or maybe neutron star mergers, places where there's a sudden, incredibly dense flood of neutrons. Nuclei just soak them up really fast, faster than they can decay, building up to very heavy elements.
Okay, and the S process?
S for slow neutron capture. This happens in less dramatic environments, like inside those AGB stars, asymptotic giant branch stars. Neutrons are captured more slowly, allowing time for radioactive decay steps in between captures.
So different processes make different isotopes.
Exactly. And Rehder also mentions the RP process, rapid proton capture, the new RP process involving neutrinos, and the gamma process, photodisintegration, where high-energy photons knock particles out of nuclei. They all contribute to the mix of elements we see.
It's like a whole ecosystem of element creation.
It really is. Different stars, different stages, different explosions, all adding their bit to the cosmic inventory.
Chapter 3 also zooms out to look at galaxies: elliptical, spiral, irregular.
The basic types. Our Milky Way is a spiral galaxy. He gives some stats, size, structure, mentions Andromeda, our nearest big neighbor, and the Magellanic Clouds, smaller satellite galaxies.
Just reminding us that stars live inside these huge structures.
Right, and the galactic environment matters, how crowded it is, how much gas is around. It all influences star formation and evolution.
And finally, Chapter 3 touches on how stars end their lives.
Depends on their mass. Stars like the Sun, or a bit bigger, eventually puff off their outer layers as a planetary nebula, leaving a white dwarf behind. That's the AGB phase connection.
But more massive stars.
Much more dramatic. Stars maybe 8 times the Sun's mass or more end in a supernova explosion.
Which is crucial for spreading those heavy elements.
Absolutely critical. Supernovae seed the interstellar medium with everything from oxygen up to uranium. And what's left behind can be a neutron star, sometimes spinning rapidly as a pulsar, or if the star was massive enough, a black hole.
So stellar evolution is this amazing cycle of creation and dispersal.
Birth, life, death, and recycling. It's what drives the chemical enrichment of the universe over billions of years.
Okay, let's venture out into the space between the stars. Chapter 4, the interstellar medium. The ISM, it's not empty, right?
Far from it. It's this mix of gas, mostly hydrogen and helium again, but with traces of all those heavier elements ejected by stars, plus tiny solid particles called dust grains. And remarkably, quite a few molecules.
Even organic molecules.
Yes, surprisingly complex ones too.
And the ISM isn't just one uniform thing. Rehder talks about different phases.
Right. You've got really hot, really thin gas, sort of like a cosmic corona, then warmer, diffuse neutral clouds. And critically, these cold, dense regions called dark clouds or molecular clouds.
Dark because they're full of dust that blocks visible light.
Exactly. And it's inside these dark, cold clouds that the most interesting, complex chemistry happens.
Why there specifically?
Because they're shielded. Starlight, especially damaging UV radiation, can't get deep inside, so molecules can survive longer. And the chemistry isn't driven by photons.
It's driven by cosmic rays. High-energy particles.
Primarily, yes. Protons and alpha particles mostly, zipping through the galaxy. They collide with atoms and molecules inside the cloud, knocking off electrons, breaking bonds, and kick-starting chemical reactions.
And this leads to a whole zoo of molecules.
It's a really diverse zoo. Rehder lists examples: water, carbon monoxide, ammonia, formaldehyde, methanol, methane, right up to things like cyanodecapentane, Hg10CN, 10 carbons, and a nitrogen.
That's huge for interstellar space.
It is. Shows what can happen even in these extreme conditions near absolute zero, very low density.
He also mentions fullerenes being found.
Buckyballs.
Yeah, C60, even bigger ones called bucky onions. Detected in space and also found preserved inside meteorites, which tells you they were around when the solar system formed.
And the dust grains themselves, tiny, right, nanometers to micrometer.
Tiny, yeah, and often coated with ices, frozen water, CO, CO2, methanol. These icy mantles on the dust grains are incredibly important.
Like little laboratories. Exactly. Rehder really emphasizes their role. They provide surfaces where atoms and molecules can stick, meet each other and react.
Especially for making molecular hydrogen, H2.
Crucial for H2 formation. It's hard to get two H atoms to stick together in the gas phase, but on a dust grain surface, they can meet, react, and the grain absorbs the excess energy, letting the H2 molecule form and escape.
So the grains are catalysts and also shields.
Both. They shield molecules from UV and they catalyze reactions. They're active players in interstellar chemistry.
Okay, what kinds of reactions happen in these clouds? Rehder lists a bunch. Ion-neutral reactions?
Yeah, these are really important and often very fast, even at low temperatures. Cosmic rays create ions, and these ions then react readily with neutral molecules.
And this H3+ ion is key, triatomic hydrogen.
H3+ is often called the king of interstellar chemistry. It's formed from H2 and cosmic rays, and it's a great proton donor. It reacts with almost anything, passing on a proton and initiating chains of reactions.
What else? Dissociative attachment.
That's when an electron sticks to a molecule and causes it to break apart. Radiative recombination is an ion and electron getting back together, releasing a photon. Radiative association is two things sticking together and releasing a photon to stabilize the new molecule.
Important for building bigger molecules.
Yes, especially in low-density gas where three-body collisions are rare. You also have electron attachment, photodetachment, charge transfer, and just plain neutral reactions. It's a complex network.
Rehder gives some basic pathways, like for making carbon monoxide, CO.
Right, starting from C+A, the ionized carbon atom. It doesn't react easily with H2 directly at low temperatures.
So how does carbon get into molecules?
One key step is C+ reacting with H2 via radiative association to form CH2 plus C. From there, reactions with more H2 or with oxygen atoms can lead eventually to CO, which is super abundant.
And similar pathways for nitrogen compounds like ammonia precursors and oxygen compounds like water precursors.
Exactly. Starting with the initial ions formed by cosmic rays like N+ or O+, and then building up through sequences of ion-neutral reactions, hydrogenation, and recombination.
What about the really complex stuff, those long carbon chains, polytines, and cyanopolonies?
Those are thought to form mainly on the surfaces of those dust grains we talked about. Atoms like carbon landing on the grain, reacting, maybe getting hydrogenated, forming chains, and then eventually getting released back into the gas.
And silicon chemistry, too, making silica dust, silicon carbide.
Yep, SiO, silicon monoxide, is seen in the gas phase, and it's believed to be a key precursor to silicate minerals and silicon carbide, which are major components of the dust itself.
So how do we actually know all these molecules are out there? We can't exactly grab a sample.
No, we rely on spectroscopy, observing the light that comes from these clouds or the light from background stars that passes through the clouds.
Looking for fingerprints.
Exactly. Molecules absorb or emit light at very specific wavelengths or frequencies, corresponding to changes in their rotation, vibration, or electron energy levels. Each molecule has a unique spectral fingerprint.
Like barcodes for molecules.
That's a great analogy. And we need laboratory measurements here on Earth to measure those barcodes accurately for known molecules. Then astronomers can compare the lab data to the signals they detect with telescopes. Theory helps too, predicting spectra for molecules we haven't made in the lab yet.
So it's a real synergy between lab work, observation, and theory.
Absolutely essential.
Rehder then focuses on some key species, hydrogen obviously,
Yeah.
atomic H, HI, ionized H, HI, H2, H3+ mel.
All the main forms. He explains how UV light ionizes atomic hydrogen near hot stars, creating HII regions, how cosmic rays and high-energy photons break apart H2 and ionize it, leading to that crucial H3+ ion.
And H2+ drives the chemistry.
And drives a huge amount of it through proton transfer reactions. He also mentions ortho and para forms of H2 and H3+ atoms.
Spin isomers, do they matter much?
They have slightly different energies and sometimes different reactivities, especially at very low temperatures. The ratio of ortho to para hydrogen can even be used as a kind of thermometer for the clouds.
Interesting. Then carbon monoxide, CO. Second most abundant molecule after H2.
And super important as a tracer. We detect it easily through its rotational transitions at radio wavelengths, also in the infrared and UV. Because it's bright and widespread, astronomers use CO to map out the location, density, and motion of molecular clouds across the galaxy.
And the isotopes of carbon in CO, 12C versus 13C?
That ratio, 12CO, 13CO, tells us things. It's different in the interstellar medium, maybe around 70, compared to our solar system, where it's closer to 89.
Why the difference?
It reflects different amounts of stellar processing stars make 12C and 13C in different ways and in different amounts. Also, chemical reactions at low temperatures can slightly prefer one isotope over the other, changing the ratio in specific molecules. It's a clue to the history of the material.
He also mentions other molecules like CN, the cyanogen radical.
Yeah, another readily detected molecule, often seen alongside CO, giving more clues about the chemistry.
Okay, let's wrap Chapter 4 with the evidence for dust grains. How do we know they're there?
Several ways. One big one is interstellar reddening. Dust absorbs and scatters blue light more effectively than red light.
So starlight passing through dust clouds looks redder and dimmer.
Exactly. We also see infrared light emitted by the dust grains themselves. They absorb starlight, heat up a bit, and then re-radiate that energy at longer infrared wavelengths.
What else?
Polarization. Starlight passing through dust clouds often becomes partially polarized, meaning the light waves tend to align in a specific direction. This suggests the dust grains are not spherical and are aligned by interstellar magnetic fields.
And depletion.
Ah, yeah, that's crucial. We see that elements like silicon, iron, magnesium, calcium, even a lot of carbon and oxygen are missing from the gas phase in dense clouds compared to their overall cosmic abundance.
Where they go?
They're locked up in the solid dust grains. That's strong evidence that the grains are made of silicates and carbonaceous materials and iron compounds. Even deuterium, heavy hydrogen, is depleted, suggesting it's being used in chemistry on the grain surfaces.
So multiple lines of evidence pointed to these important little particles.
Definitely. And Rehder circles back to their vital role in making H2. Hydrogen atoms hit the grain, stick for a bit, find another H atom, react to form H2, and the energy released kicks the molecule off the surface.
And the grain surface acts like a catalyst, a meeting place.
The essential third body needed for the reaction to happen efficiently in space. Without dust grains, we wouldn't have nearly as much molecular hydrogen, and the universe would look very different.
What are the grains made of specifically?
A mix, as inferred from the depletion and from their infrared spectra. Silicate minerals like olivine and pyroxene, carbonaceous stuff like amorphous carbon, maybe graphite, and those PAHs, polycyclic aromatic hydrocarbons, possibly some iron compounds too.
PAH has specific infrared signatures.
They do. Characteristic emission bands in the mid-infrared that are seen widely in the ISM, providing strong evidence for their presence. Silicates have their own features too, around 10 and 18 micrometers.
And finally, he mentions complex molecules forming on these grains, like amino acid precursors.
Yes, things like aminoacetonitride, which is just a few reaction steps away from glycine, the simplest amino acid. Lab experiments simulating interstellar ice conditions show these kinds of molecules can form via radical reactions on icy grain surfaces.
So the building blocks of life might literally be forming out there in the cold, dark clouds.
It's a definite possibility and one of the most exciting aspects of interstellar chemistry. These molecules could then get incorporated into comets and asteroids and potentially delivered to young planets.
Amazing stuff. We've covered a lot of ground. The Big Bang, stars, the interstellar medium. That takes us through the first 4 chapters of Rehder's Chemistry in Space.
Yeah, a good foundation. Next time, we'll dive into our own cosmic backyard, the solar system.
Sounds great. We'll explore the chemistry of planets, moons, asteroids, comets. Should be fascinating. Join us then for the next part of our deep dive.